Thank you very much for joining this episode of SPCL Bcast in about the middle of our season. I'm super happy that we could convince Oskar Mencer from Groq and formerly Mencer, as you can see on his shirt that he's wearing, to tell us about the Groq capabilities, and this time on IEEE Floating Point, or no IEEE Floating Point. So I'm very curious to hear about that, and I give it to Martin to introduce him a little bit more.
Thank you. Oskar obtained a PhD in computer engineering from Stanford University in the year 2000. He then joined Bell Labs, and after leaving Bell Labs, he became EPSRC Advanced Fellow at Imperial College London. He then started Mencer Technologies, which was recently acquired by Groq. So without further ado, the stage is all yours, Oskar.
Thank you very much, and in particular, thank you, Thorsten, for inviting me and for forcing me up a mountain all the way to the top in Switzerland before that, which was a grand experience, and I recommend to anybody. So maybe I should start with the title. I picked a very strange title here because of historical background. When I was a graduate student and I was getting my PhD, I was told that everything would have to be done with IEEE Floating Point forever. World has fought hard to establish the IEEE Floating Point standard, and it was the most important thing for computational scientists to insist on IEEE Floating Point. And I was convinced as a young student that there are more efficient ways to do computations. There are more efficient ways to use bits. There are more efficient ways to use computational resources. And I was thinking that computing was ready for a deployment in the infrastructure of the world in which efficiency would be the number one concern and requirement as we are building out infrastructure around the world: bridges, roads, electricity, water. Efficiency is the most important part. And I couldn't have been more wrong. And so when somebody is wrong, it's important afterwards to say, look, I was wrong about this. As a young person, you think the world is changing very quickly. I saw computing everywhere. But we were, in fact, nowhere. There was no computing as infrastructure in 2000. And in fact, rather than getting rid of IEEE Floating Point, we continued to push down the line of writing all our software with the most inefficient instruction set that the world has ever seen. There has never been, and hopefully there never will be, as inefficient an instruction set as the Intel x86 instruction set. And as computer architects, you of course know that and then just have to shake our heads all the time. But it's tremendously inefficient in terms of hardware, energy, the effort that is needed to decode decades of updates and upgrades of the instruction set so that you can run a program written in 1970, 1980, 1990, 2000, 2010, as well as now. So that has grown as an inefficiency thing. And so I thought, well, x86 is going to be out the window very soon, and IEEE Floating Point will go with it. And we are now 24 years later, and we are now slowly seeing that happening. We saw Windows being challenged by Linux, and we are now finally slowly seeing the x86 platform being challenged by much more efficient instruction sets with compute chips being built at the big cloud providers, as well as, of course, with embedded processor companies rising up to the HPC and the data center challenge and giving us efficient instruction sets. So without delving too much into this, let me go forward to the next slide, if I know how to do this. Yes, here we go. Can you see the whole slide, or is there something blocking the slide on the right?
You can see the whole slide.
Okay, great, great. So, as was mentioned, 2 years ago, my tiny little company, swimming against the grain of computer architecture for 20 years, has merged and joined with Groq in California. Groq is a fantastic company that is building a chip that works along very similar principles as I have dreamed about when I was a graduate student in the late 90s, as well as the architectures that Mencer has been building for custom applications, where we were building custom architectures for each of the applications that we were encountering. And for 20 years, we were building custom computers for customers who could afford them or who had a need for efficiency. And the surprise to me for 20 years was that the need for efficiency did really not exist in computing until last year. Nobody cared about how much it costs to compute anything. And that will come as a surprise to students in computer engineering, because we are all taught and we think that it matters, but it doesn't. Or it didn't, to say it in a better way. Since last year, we have large language models, and large language models have bridged between humanity and computer people, talking zeros and ones, programming languages on the one side, human language on the other side. We thought it is completely impossible to get to human languages, as we tried for many decades. Suddenly, out of nowhere, we got computers that speak human. They create human language. They create a bridge. And for that, we now need infrastructure in governments, for large corporations. And that infrastructure needs to be efficient. You look at the two chips here, you see what happened when you build multi-core processors that probably many people in the audience admire and like and learn how to build and really want to advance. And you can see how a chip looks like on the left that is built on static data flow principles. What I mean with that is the thing on the right with the multiple processors is a dynamic chip. It never knows what is going to happen next. It's event-driven. In fact, it's described with an event-driven simulation language, usually, which is a disaster by itself, right? Either Verilog or VHDL, but this talk is not about that. Microprocessors take events as they occur and try to do the best they can to deal with them. Most of the circuitry that you see here on the right deals with these events that occur while the program is running and tries to be smart about what it does with it. On the left, the chip consists of memory, arithmetic units, and a switch network.
Are you there, Oskar?
For every nanosecond, for every one of these arithmetic units or memory items, what they're going to do and how they're going to behave. And that gives a static, predictable, fixed runtime that is the same every single time you run a program on it. And it also is what I call a local energy minimum and a local cost minimum if we go into the economy of things. And then it will be clear later on. So let's move on to the next side, how does this work? So here's a little video I will try to play that demonstrates the principle. Can you see this video? Does it work?
Yeah, we can hear it and see it.
All right. So this is what happens when you pre-schedule. You know exactly what is going to happen. Every time I run this program, it will happen exactly in this way. I can stop this. I can reverse the movie, right? We can start it again. Okay, here we go. It does exactly the same thing. That's what you get when you run a Groq program. Now, the interesting part is that program doesn't just run on one chip. It can run on hundreds of chips all together, all scheduled at the same time, with a proprietary cable that goes between these chips. So you have a rack level, statically scheduled machine. And you can imagine the engineering challenges of synchronizing hundreds of chips to be running in lockstep on the nanosecond level, right? It's fantastic. Nothing like this has ever been done before. So you can see I'm quite excited. Here is the electrical engineering view of this. This is the chip. You have SRAM in the middle, and you have a switch matrix, and the data goes in and out from the middle. So there is a clear orchestration of flow of data, and you can watch it on this tool, which is essentially a program running on a Groq chip. And you can watch where your data items are going, how they behave, and where you might have a bug, where you might have some problem. You can play that forward and backward, step it. It's just more fun to play it at full speed in a presentation like this. But a lot of fun is to be had with such things. So then we have to jump forward. This is all kind of engineering talk, and nobody cared about me saying that static data flow is 100 times faster, 100 times more efficient. You know, story's been told for 20 years. But today we have something that people actually care about. People care about language. And we can say that this thing generates language at 10 times the speed of an NVIDIA GPU. And the fans and proponents of GPUs can stand on their head, they can jump around in a circle, they can dance any dance they want. It is 10 times faster. There is 10 times more words coming out per second than out of GPUs. And literally, there is nothing that the GPU community can do to change that, other than, of course, build new chips and maybe custom hardware, put other things inside. But right now, as it stands, the advantage has been measured by many, many third parties. So it's not even us. We are not measuring performance. We are not going to tell you how much faster it is or isn't. We let other people measure. There is the web service, and you can send your query to OpenAI. You can send query to the Groq cloud, and there is a large language model out there that speaks at a certain speed, which is at least 10 times faster, and sometimes a lot faster, depending on the model, than OpenAI. So now that we know it's faster, let's have a look inside and see how it actually works. My talk is not about that it's faster. I just wanted to start with the general principle of why this is a good idea. But if you look inside, you see data types. And you see many different data types: uint8, int8, bool8, uint16, int16, bool16. And you can imagine many, many different data types. There is even a float 16. And there is a float 32 here as well. Now that float 32 is not an IEEE float 32. It has advantages and disadvantages. At the end of the day, we look at the quality of the generated words, and we look at the speed at which the words can come out, and we are quite happy with it. And so my talk is going to be a little bit about this world of flexible bit width, of flexible number of bits, of flexible representations, and how one can adapt computing to having different types of computing infrastructure, different bits inside of that. And so in order to do that, we have to step back. Maybe before we do that, just to show the concept of the 32-bit floating point, which is really a combination of lots of 16-bit floating point computations. So it turns out that you can do 32-bit floating point by using 16-bit floating point. And we have here the way you have the 32-bit input. It gets split into 16-bit. You have a matrix multiply of two 16-bit floating point numbers, creating a FP32. You have another one with the lower half, and then you concatenate to get the result. So very nice. One 32-bit can be done with two 16-bit floating point multiplications, as long as they generate a 32-bit result, of course, each. So, so that's very good news. And a lot of combinations and things can be done with these units. But then what is the precision of that computation? And here there is an interesting graphic of what Groq calls true point. And it's a Groq trademark, something that Groq has been working on, which is looking at matrix multiplication. You have a lot of additions along the row or column, which are accumulations. And these accumulations have a problem. As you accumulate more and more, and anybody who's written an accumulator before knows that, you have a problem with very small and very large numbers, and the floating point coefficients or the exponent moving the numbers around, so that you may not have an overlap between the bits that you have about your numbers. Imagine you have a very large and a very small number, and you want to add them up in floating point. You lose the bits. Why do you lose the bits? Because some of the bits are here, some of the bits are there, and they just disappear on you. So in order to fix that, Groq has a very large integer adder, which costs nothing in terms of space on a chip. Integer addition is close to free, especially if you don't have to do a tree adder, but you do a slow adder. So you're accumulating slowly across a large number of bits in one particular part of the computation where you need a lot of bits and no exponent, right? So these are the kind of things. Groq TruePoint is not completely public, and I can't show exactly how it works. Unfortunately, I would love to. But you can see here the residual mean square error of a dot product. And you can see FP32 with NumPy. Usually the trick is you sort your numbers first so that you don't get big differences. And so you get an error with a sorted array of FP32 numbers with NumPy. And then you get Groq TruePoint, which is down at the bottom. So this again is to show that by customizing the representation for the different variables, for the different parts of your program, you can achieve miracles numerically. It requires thinking, it requires caring, it requires wanting to do a good job with assigning bits to every single one of your variables. And even though I've been doing that for 20 years, I have not seen too many universities actually show any interest in teaching how to assign different bit widths to different variables. There are a few research efforts that have been around, but generally, until now that we have special chips with different bit widths, now we are starting to see some interest, and people are digging up papers from Stanford where the idea has been taken to an extreme already 30 years ago by geophysics people who showed that you can do geophysics simulations with 1 bit. 20, 25 years later, this is a huge novelty in the AI world, and people who have not been alive when the original work was done are rediscovering that, hey, you could be computing with just 1 bit for every variable. That's really exciting. Of course, there's problems with that, and maybe 1 bit is not optimal, causes a lot of problems. So one of the things that I've been working on over the last few years is to connect the Groq technology on the one side with FPGA technology, which we have been using for many years, where on the FPGA side, we can have any bit with any representation, any encoding of numbers into zeros and ones that we want for the computation. On the Groq chip, we are limited to particular ones. With the combination, now there is FPGA cards, Groq cards, all statically scheduled together according to the principles before, where you can have any number representation on the FPGAs. And you can use the specific number representations that Groq offers to cobble together the precisions, the representations, and ultimately the results that you would want to get. So this is kind of the state of this. For anyone who is interested, just as I graduated from Stanford, I laid out a lot of these ideas in a talk, and I naively called it computing with FPGAs, because I didn't know what would be wrong with that, and laid out what became the basis for Mencer, as well as a lot of research that followed, and which today is relatively common knowledge in the AI chip community, that you can use lots of different number representations to get an advantage, to get an edge. But of course, for 20 years, this was heretic. So when I interviewed at that time with this talk in 2001, when I interviewed at ETH, there really was no understanding or interest whatsoever in any of these topics. It was actually considered slightly high risk to be talking so much against the establishment of computing at the time. So why don't we go back to basics? So let's imagine we can use any number of bits for any variable. And let's make our life simple. We just want to approximate a function. So you have sine, cosine, log, normal distribution, gamma function, whatever it is that you want to calculate. Simple function, one variable in, one variable out. Very easy. Should be trivial. What kind of bit widths do we need inside of the computation, and which method are we going to use? So I looked at something very simple, polynomial. We know we do function approximation with polynomials. But how many bits do we really need for each one of the coefficients inside of a polynomial? You can ask Chebyshev, you can ask Remez, you can ask any of the great mathematicians out there that were working for decades on polynomial approximations, and they have absolutely no opinion on the subject. There is no information theoretic treatise of which information content really exists inside of these coefficients. How many bits do you really need? Of course, today we have neural networks. These coefficients are coefficients of a cell in the neural network. And we care about efficiency. So people are starting to ask these questions. What are the bits that are needed? This is work from 2005, now over 2 decades ago, because as you know, publishing something in IEEE transactions takes many years of back and forth to explain to reviewers what it is that the paper is trying to say. So it took many, many years, and then finally it came out in 2005. And we were looking at different methods and found that for different bit widths, and depending on the area, latency, or throughput that we are interested in for these units, the different methods have different behavior. Polynomial, a linear term plus a table, or a quadratic term plus a table. 3 simple methods. So just to simplify life. Of course, there are 20, 30, maybe 100 different methods to calculate these functions. But, you know, to make our life simple, polynomial plus some table. You look up in a table, you look up the coefficients, you push it through a polynomial, you get it out. How many bits do you need, right? Should be trivial, but there is no math out there that would tell us the answer. Here, just to show the structure, so you have bits coming in, you split it into 2 parts, you go into a table. In the table, you read all of your coefficients. The coefficients go into a polynomial, and then you get the result out for a function. Very standard kind of easy way to do this. And so the only way we could do this was brute force, build them all, create the circuits, synthesize the circuits, run the circuits, measure the area of the circuits, and then see what happens. And so here you can see if we need 8 bits of precision with 16 bits of range, and we want to compute the sine function, the result is that it is best, optimal, to use a table plus a polynomial of degree 2 with 19 bits. Okay, why 19? Well, it's hard to tell, but for the log function, it's just 12. And for the square root function, it's 18. So there's a wild amount of numbers here, which were all automatically generated with a hardware generation system that at the time I wrote in C++, which would generate hardware circuits from a programming language automatically, and then generate these results in the tables and the measurements. I actually tacked on a latex part onto my piece of software where the paper would come out from the synthesis tool. So we have the software that generates the circuits, but the end result was actually the LaTeX with the figures, with all of the different variables and all of the different variations of the circuits, drawn graphs and plots, and generating a paper that very quickly can be turned into a conference paper. And so I was thinking, what's the most efficient way to generate a conference paper and get it accepted? And I got it down to under a week. And you can see, since I could automate it and the paper got accepted and really a very good mention in the conference, and people were quite amazed at what we've done, I kind of lost interest in publishing, because if a paper can be generated automatically by a computer program and nobody knows how we could have possibly achieved that in half a year to a year's worth of effort, it became less interesting to publish papers. And I thought, well, why don't we build machines and sell them to someone to use? That could be more difficult. Maybe that's a bit more of a challenge, because you're going to get people to actually pay for something that's completely off the chart, different from anything else that anybody else is selling. So that was exciting. And we did that. On the theory side, I kept thinking, what is the theory behind all of this? And talking to a lot of scientists, physics and mathematics and other departments around the world, I kind of settled on that there is really a space, time, and value space or environment. We know in physics, we discretize time and we discretize space into dots, right? Into places in space. And then we run numerical algorithms on this discretized space and time. But what if the space and the time discretization was changing over time? And we were also changing the number of bits we are using to represent the variables. As you're simulating a system, you're optimizing a function, you're gaining more and more information. At least that is a conjecture. As you're gaining more information, you should be using more and more bits. In the beginning, you know nothing. So as you know nothing, you pick a random point, maybe in some mathematical, more advanced way than the Euler method. But the Euler method is still the same. You pick a number and then you go from there. But that initial number you picked was a random guess. You don't need to use 64 bits or 274 bits to represent that random guess. As you're computing, you're learning more and more, and you can increase the discretization, not just of space and time, but also of the value of your variables. And so for anyone looking for a PhD topic, I think there is still at least 100 PhD theses in this, because this can be applied to many different parts of science, of engineering, and of course now for AI. A lot of theoretical breakthroughs are still waiting in developing a mathematical model, an engineering model, and the scientific model for how to deal with variable representation, encoding of individual variables inside of a computer program to optimize computation. You can see here on the right, there is the spatial grid, and you can see how I'm imagining a three-dimensional space with discretization of space in one dimension, discretization of time, and discretization of the value of each one of these variables. And you can see just from a matrix multiply how important it is. The sum across the row has to be a completely different representation than the coefficient, the multiplier into that sum. So a lot of work that could be done there. Here is a result from a journal paper that we published together with an oil and gas company and Stanford as well, to show compression ratios of matrices. Here we were solving a fluid dynamics problem and representing the problem through sparse matrices. And then we were encoding these sparse matrices into different compressed versions. And the compression here really is number representation. So each one of the numbers has a different number of bits. And you can see as the compression ratio goes to the right, we get a different amount of speed up. So the speed depends clearly on the compression. And the more you compress the numbers, the faster you can compute. And then we implemented the solution by starting with a extremely highly compressed number system setup. And then as we optimized the fluid flow space, we were creating denser and denser spatial grids and used more and more bits for the variables inside. And with that, we could increase the speed of the computation dramatically beyond what the computational physicists were doing at the time. So it's a very exciting result of fluid dynamics fluidly changing the discretization across the whole computation. Fantastic project, really, really exciting. So then we go back to LLMs and looking at tokens. Tokens represented, of course, with bits. and asking ourselves, what is good enough? And that is something that computer scientists usually don't like to hear, because in computer science, we don't know what makes a result in geophysics or in medicine or in mathematics or in a television broadcast good enough. What is good enough? What does it mean to be good enough, right? Because if we could define good enough in a computer science way, the entirety of complexity theory would be put on its head, because we are now doing an information theoretic analysis of what it takes to find a good enough result for a particular computation. So it's a lot of opportunity there. With LLMs, we now understand, the quality of the conversation, and we can match the conversations across multiple ones. Good enough, is it to get the same token sequence? How many bits do we need to represent all of the tokens, really? And how many choices for the next word in a sentence do we really have, right? We cannot put together all the different sequences of tokens. They don't match up. They don't create correct language. We're currently encoding grammar into the LLMs. They're learning about what can go after what. But that could be done a lot more efficiently as well. Because we already know, we could prune the space and say, well, we know that many combinations don't work. You cannot put the word is after the put R, after the word R. You cannot have two R's one after the other. That makes no sense whatsoever either. So many different things that can be done by looking at the encoding of the information, what makes information good enough, and what the purposes of that computation. So to remind ourselves back, the goal is to accelerate the generation of language, and do that by using static flows where we can address each one of the points in that static flow, and the information theoretic bandwidth of the bandwidth of information, if you want, through each one of the nodes in order to achieve a result. The interesting part for me here is that the Groq chip is built with transistors that are infinitely larger than what OpenAI is using. I believe this would be 7 nanometer on the OpenAI side, and we are using I think I don't even know, maybe 16, 20, 24, whatever the nanometers are, a very large process manufacturing the chip in the US, where no 7 nanometer chip today can actually be manufactured in the US. So that changes the location where you can manufacture these chips. But the cost, of course, is also orders of magnitude different. So not only do you have the speed advantage, but this is built out of toy transistors. So a lot of potential, a lot of opportunity, whichever way you want to push that. And of course, then the encoding of these large transistors has different meaning. So given that we need to leave some time for questions, I would like to finish up here and invite people to reach out to me after this talk. I think I've just kind of scratched on the surface of a few topics, introduced where Groq fits in the whole space of encoding variables with bits. And yeah, let's hear any questions, any complaints, any good or bad. Yes, I can see a raised hand here. I don't know. 2 participants. Are you going to select who's asking a question, or how does it work?
Yeah, I will be selecting people.
Okay.
Timo, you can ask. We cannot hear you actually right now. Maybe maybe you can put it in the chat, worst case. Let me ask to unmute Tiancheng then.
Hello, Oskar. Thank you for this nice talk. So I have some question about the slides 17, the last slide.
All right, all right.
Yeah, 17,
Here we
yes.
go. Yes.
So you mentioned that the decoding time, the speed of Groq chip is like 10 times faster than OpenAI. So do you have an idea of how big, how large the model of the OpenAI GPT-4 is? Like, is it like 10 times or even 100 times larger than the model you are using?
Oh, this is just an example of a comparison that is public, that is out there. There are many of these. I just picked a random one, and I can see here you're asking that there is a difference between the Mixtral and the GPT-4, of course, size of the model. We've seen the 10x difference across all models using the same ones. So we of course don't have GPT-4, but there are many different comparisons out there that you need to look at in order to get. So that's why I'm not going to talk about how much faster exactly it is and how much I've measured, because I haven't measured any of it. It has been measured by people out there. There are many competitions out there where you can look at the different technologies for AI inference. I've just kind of been asserting it. So that would be a whole other talk to delve into all the different ways of comparing, and that was not the purpose of my talk here. But you are right; these are different models.
Yes, thank you. So I have a follow-up question. So, how many Groq chips do you need to get such speed?
Oh, a lot.
A lot.
You need a lot of Groq chips because you're holding everything in SRAM.
Like a few racks?
Yeah, probably.
For a model of this size. So, like, I mean, you know, the Llama 3 that they will release a 400 billion parameters model. So if you want to serve that, you need more racks, I guess. So do you see if there's any limitation there that you have to scale the number of chips with the model sizes, while for GPUs, even though they have slower HBM access rate speed, but they can like hold bigger models with much less chips?
So the solution here is very radical, right? Imagine the amount of bandwidth that you can get if you have 100 chips with SRAM compared to one chip with DRAM. And so there's really an economic argument on the large scale as you grow the whole thing. Imagine you're building 100 data centers, right? And in each data center, you want to put 1,000 racks. And you want to serve a population of I don't know, let's say maybe 4 billion people with language tokens, right? We see that the economy of scale in terms of the number of tokens produced, in terms of cost, in terms of energy cost, and the speed at which these tokens are being generated is widely different. Now it depends on how exactly you do this. And again, I didn't do a systems comparison here. I gave a talk very, very wisely on representations of variables, because Groq is in the middle of deploying this technology, and of course it's not possible to share everything right now. So it's always difficult for me to stay away from the commercial activity and stick to scientific content. But the exercise is really for you to do if you compute, and you can just think of it as computing from SRAM versus computing from DRAM. You have tremendous challenges with the current DRAM technologies, their supply chain issues, their volume issues. There is a whole set of problems that one is faced when trying to deploy 1 million chips. And so it's really not so scientific or kind of engineering focused. It's more commercially focused. Let's have somebody else also ask maybe more on the bits side. Who's going to go next? Yes.
Lex.
Hi. So I have I fully thank you very much for the talk. It was very interesting, and I fully agree that focusing on data flow, and there's a lot of performance to be gotten out of static data flow analysis. But in this area, my question would be, what is the amount of work needed in changing the programs or rewriting the programs to be able to use this architecture? So is it a completely full rewrite, or is it something where you can use some of the existing things?
So because the chip was very easy and quick to build, 90% of the effort at Groq has been on the software side. The interface is Python, and you can use TensorFlow or PyTorch and go into Onyx, or you can write your own Onyx from your own tools. Onyx, for people who are not in the AI world, is ONNX, and it's an internal graph representation of computations in the AI world. And we compiled that Onyx directly onto racks of Groq chips. So you don't need to do the parallel programming that you're doing with CUDA, but the entire machine is tackled by one compile, by one kind of partitioning of everything onto all of the chips. And we're very proud of our software stack. It really is very, very significant to be able to take Onyx graphs and then compile to a whole rack or multiple racks of machines. And we are even running statistics on how long it takes us to compile a new model when somebody comes out with a new LLM. We are typically in the 2 to 3 day range. So it takes 2 to 3 days, and we have it ready compiled, while the CUDA people are still writing kernels for weeks on end. So there is also a faster turnaround through the software architecture, which is enabled by this static schedule, of course, because it's all just solving a optimization problem, right? Usually kind of some kind of linear programming problem that you solve across all the resources, time steps, and boom, you throw out a schedule, and it can run on multiple chips at a time. So quick answer: Python, PyTorch, TensorFlow, Onyx, compile, and off you go.
Thank you very much. Thank you very much. That answers my question. Thank you very much.
Great. Ben?
Thanks a lot for the nice talk. So I have 2 questions, particularly regarding this value discretization and kind of good enough question that you alluded in this talk. So firstly, the idea sounds really interesting. And one thing that when you talked about value discretization and this good enough question, one thing that came to my mind was that in numerical analysis, there's a large a body of literature in research regarding convergence properties when it comes to spatial as well as temporal resolution, right? And I wanted to ask a bit the value discretization and good enough question, how it ties to these kind of existing numerical analysis. So for example, convergence properties of spatial and temporal resolution, I think there's a lot of research there, but
Yes.
do you feel like this good enough question is kind of
Yes.
not really being addressed properly, or?
Yes. So I was working with oil companies on that question. Funnily enough, I was surprised that I would end up with oil companies, but they're the ones with the most significant mathematicians and capability on this front out there, even though it may not be very public. So they have layers. There is the layer of mathematicians, at which point everything is infinite precision. Then they have the layer of geophysicists. Then they have a layer of computational scientists. Oh, I forgot the geologists. So first you have the geologists, then the mathematicians, so geologists look at rocks. They actually play with stones and juggle them. The mathematician looks at numbers, then the geophysicist, then the computational scientist, then the computer scientist, and then you have the guy who's optimizing the CUDA programs for whatever purpose he needs to do. At the end of the day, they bring the image that has been calculated back to the geologist who has nothing to do with computers. And the geologist walks around in the nature and looks at the rocks, drills holes, looks at the different layers, and they show him the picture. And then they show him two pictures. And he says, this picture is good enough. This picture is no good. Rocks don't do this. And on the other side, yeah, this looks kind of okay. That's how this is being done. So there is no scientific literature. There is no even attempt to capture that process. And you have the same thing in medicine, of course, right? You have doctors looking at images. And they say, oh, this is good enough. I can see what I want to see here. You can see exactly this and that. Over here, no, I can't. People, of course, try their signal-to-noise ratio. There is all kinds of filters you can run on images. You can run minimal error, average error, maximal error, statistics of errors across the image. None of that gives you the good enough metric from the person looking at it, unfortunately. So again, lots of opportunity to sit down with all of these different people in the real world, hear how they do their jobs, and create new science, create more inclusive science that considers all of the different bits and brings it all together into an engineering optimization to solve a real-world problem of optimizing these pieces of software. And you're completely right, convergence off the chart. Nobody knows how to deal with convergence once you change the number representation in the bits. A very simple experiment that is easy to explain was done with 64 and 32-bit floating point. There was some work done at Stanford, simply because I'm more familiar with the work there, I'm sure many other places as well, which ran optimization algorithms on 32-bit on single precision floating point first, and then towards the end of the optimization moved over to double precision and studied at which point of the optimization does it make most sense to flip to double precision to continue to converge to the same result. That's also now 20 years old at this point. There is a huge amount of opportunity. I think a whole branch of mathematics could be created by thinking of mathematics in space, time, and value, as opposed to mathematics with infinite precision, as we are simulating in like MATLAB or Maple or whatever mathematical software. So yeah, absolutely great question and huge opportunities out there, I think.
Thanks a lot. It also reminds me a little bit of climate and weather research, where you have this layering of different experts and sometimes missing a little bit the whole strain through the whole kind of pipeline. But maybe then to follow up. So I think the idea sounds really interesting, But then you showed this table and you kind of mentioned that you needed to use a brute force algorithm to kind of find out these optimums.
Yes.
And I feel like that sounds a bit scary. And I was wondering a bit whether you have seen or whether you feel like that maybe there would be systematic patterns emerging out of, let's say, this table where you can say, well, temperature has a certain distribution, so likely a table with quadratic is needed.
Yeah.
Or wind has a different distribution, so likely polynomial should be good.
I have not pursued this direction further because I was too intrigued by putting together the whole system and taking all of these different ideas, and there are many others on top of the special bitwidth representation, and building large supercomputers that could do things that other people couldn't do. I could have, on the theoretical side, branched off into studying that question of looking at these patterns. I did study the patterns of run length encoding of binary numbers coming out of computations. There's an interesting thing about how many zeros go after each other, how many ones. If you look at run length encoding of these and study that in terms of just numerical computations, and found a connection between the run lengths and continued fraction approximations of these functions. So it is possible to convert the run lengths of these binary numbers into coefficients of a continued fraction, which is something plus something divided by something plus something divided by something, just kind of. So I've looked a little bit into some, but it's just such a large space that a lot of opportunities still there. I don't have much more than the brute force results right now.
Okay, thanks a lot. Really appreciate these insights, and thank you for the nice talk.
Yeah.
Thank you. So now Labhaschen. Hope I pronounced the name correctly. Okay, you put the question in the chat. Is the value dimension independent of space and time in the discretization space?
Oh no, I think it's very clear that it's highly dependent. That it really these are extremely interdependent dimensions. Your discretization in time sets your discretization in space, assuming some discretization in value. And if you change any of them, you have to change the others as well. I would say that it's an extremely strong dependency between these three. But the real question is not the dependency. The real question is, how do you find the optimal points? What are the most energy efficient, time efficient, or dollar efficient points in the space-time value space, given a certain technology of transistors, given a certain computation, and given a certain requirement in terms of latency, throughput, and area on a chip for the computation. So it's an optimization space with highly dependent variables.
I hope. Yep. Thanks for the talk and answering the question. We have. Oh, person, yeah, you want to say something?
No, I just wanted to say thank you. We're running out of time, so no time for my questions, but it's great.
Okay.
You can ask me questions anytime, Thorsten. I'm available. And then anybody else, feel free to reach out. I love discussing these topics and looking forward to more interactions to come.
Thank you. Thank you a lot.
Mm-hmm.
Bye.
All right. Bye-bye.